So good afternoon to everybody. My name is Pavel Kulha. I am coordinator of the project NABIAM. The project is a cross-border cooperation project between Czech Republic and Austria. The goal of the project is to establish a long-term cooperation network of contacts and relationships with relevant entities in the field of research, development, and business in the field of polymer electronics and medical technologies, with a focus on nanotechnology, biosensors, and additive manufacturing. Those three words basically creates the shortcut of NABIAM. The network, combined with the mapping of competencies in the above mentioned fields, should help us in the future to quickly create a project consortia for a specific topic and also adequately fund them through appropriate funding programs at regional, national, and European level. We have three partners in the project. The project is relatively small, just 18 months project. The coordinator is Profactor, which is non-university research company for applied production research, which is located in Steyr in Upper Austria. On the Czech side, we have a university partner, University of South Bohemia, which is a science and research center specializing in education and research in natural, human, and social sciences. In this project, it's represented by the Institute of Applied Informatics, Institute of Applied Physics and Biophysics, and Institute of Chemistry and Biochemistry. And the second partner from Austria is Business Upper Austria. This is a business agency of the Upper Austrian government. And BizUp is an innovation driver and partner for location and development and settlement of companies and cooperation in and public funding advisory services. The BizUp is represented by plastic cluster and medical cluster. Those two clusters are involved in the project. So the activities of NABIAM are basically reciprocal scientific lectures with focus on nanotechnology, biosensors, and additive manufacturing. We already had two series of such scientific lecture. One is still planned with focus on additive manufacturing. So I will for sure contact you with an invitation later. The second big topic is preparation of competence map, including infrastructure, equipment, and available technologies in the research and technology organizations in the region, and also companies in the region. So we basically conduct bilateral visits to get to know each other, not only let's say business to business, but also business to research. So we are trying to connect companies also with research groups, and those meetings are then or will be presented in webinars. One has already passed. It was focused on nanotechnology. Now we have the second webinar, which with the topic on biosensors, and there will be also a third webinar on additive manufacturing, which will take place 24th of June. And I will also send an invitation to all participants. There is also one online matchmaking event planned on 29th of June. You can register to this event. There will be partners available. You can choose according the topic you are interested in and find a suitable sensor for business to business meeting. The meetings will be around 20 minutes. And there are several slots dedicated to additive manufacturing, biosensors, and nanotechnologies. over 2 days. So the meeting is starting 29th, but continues also on 30th of June. One important part of the project is also preparation for joint projects. Of course, the preparation itself is not part of the NABIAM, but we want to stimulate the cooperation, find suitable partners, and set up the consortia. This is actually goal of the NABIAM project. So we are basically looking for partners in the above mentioned fields to cooperate or to prepare a proposal for either, again, Interact projects or Horizon Europe projects, Eranet, SME, or other national or international possibilities. So all the events are regularly published also on social media and our website. So feel free to check our website and follow us on social media, either LinkedIn or Facebook. And this is basically all regarding introduction of NABIAM. And the first speaker with the presentation topic nanotechnology in sensing is Jaromír Hubálek, associate professor from SEITEC Brno. So Jaromír, the floor is yours. We are looking forward to your presentation.
Thank you for your introduction. So,
I just want to mention I'm sorry, I mean, I just want to mention that there is a 15-minute slot for each speaker, including questions and answers. Please raise your hand using the button in Teams, and then you will be invited to place the question. So now the floor is yours.
Okay, this is a really short time for this topic, but okay, I would like to briefly introduce our results in nanotechnology used for sensing, which we obtained in SEITEC. So I will talk about aligned nanostructure formation and their applications. As well, I show you some results from spontaneous growth of nanostructures and single nanowire under measurement. And finally, I mention some nanodots and quantum dots and their application. So first of all, the properties, the basic properties of nanostructures well known. So just briefly, dimension below 100 nanometers, and then we obtain it 2D, 1D, or 0D nanostructures. So the last two I will talk mainly. So the properties is large area versus volume, and we can as well observe quantum phenomenon, which depends on the size and material used. What is important is our methods for fabrication of the nanostructures. It can be based on lithographic, which is very lithographic way, which is very expensive, of course, and as well non-lithographic methods, which I will talk mainly. So it will be based on self-orderings and spontaneous growth. So to create nanostructures without nanolithography, we developed this template-based techniques, which is based on self-ordering phenomenon in anodic oxidation of aluminum. This techniques allows us to grow or hexagonally aligned nanopores as template, which you can see on top picture, and develop this techniques was developed for thin film technology. So it is based on a sandwich structure on the left picture. So it is many structure in the process, which allows to create 1D vertically aligned nanostructure or aligned nanodots. So here are some example of the template and the nanorods from the top view and side view. So we can create using this method metal oxide if the refractory metal is on the bottom deposited, and we can use galvanic plating to fill out the nanopores, so we can obtain metallic nanostructures. The first application which we did was enlargement of the sensitive area. So it was motivated by miniaturization with this statement: by increasing the area 50 times, the sensing part of the sensor can be reduced 50 times while maintaining the same response. So here you can see some our results. Is already old results. We used some nanorods on the surface, and we characterize these structures using electrochemical methods, which you can see here. So it was impedance spectroscopy and voltammetry. So it is electrochemical method, and flat and nanostructured electrode was compared here. So you can see some benefit. It was really in the sensitivity, and enlarging the area is here clear. But the hydrophobic or super hydrophobic properties of these structures has to be avoided from the measurement when the liquid solutions are used in the measurements. But this way enables, so this electrochemical way enables using this approach for the biosensing, electrochemical biosensors especially. The much easy way is to use this aligned nanostructure in gas sensing. So here we present that it's possible to anodically oxidize alloy. So here we created mixture bimetallic nanostructures with the monoclinic tungsten trioxide and orthorhombic zirconium dioxide. So by this structures created this template-based technique, we obtained a very fast response to CO, high sensitivity to ethanol, for example, in this results. Another approach using these techniques is to formate 3D structures. So it is vertically aligned structure between upper and lower electrode. So you can see on this picture the steps to fabricate. So the upper electrode is created or made by galvanic deposition to create this ball. So this electrode is permeable to gas. And as well, the upper electrode can be split into 2 electrodes. So we obtain 3 electrode systems. So 2 electrodes on top and 1 electrode on the bottom. Very small overall resistance is obtained by this structure. Although that single nanocolumn here has very high resistance, but overall resistance finally is very small. So what was as well observed was Schottky contact. As you can see here, it can be advantageously used for the measurement method using these nanostructures. Another approach is to use spontaneous growth, which can be obtained by chemical vapor deposition. Here is low pressure CVD used for carbon nanotubes growing. When the catalytic nanoparticles are deposited on the film, on the substrate. So as a precursor, the methane or acetylene with small amount of hydrogen is used for the growth. And this film will vertically not we can set vertically aligned carbon nanotubes has very high absorption of infrared part of spectrum. So we use it to cover membrane of microbolometers, as you can see here on the pictures. It is pardon, sorry. It is uncooled microbolometer is fabricated by MEMS technology, and we increase the sensitivity 4 times using this technique, and as well detectable wavelength range was increased up to 25 micrometers as minimum. It is higher, but it is difficult to measure. Another approach is aerosol-assisted CVD at atmospheric pressure, and using organometallic precursors, we can create semiconducting metal oxide, for example, tungsten trioxide and zinc oxide, to create or to grow nanowires or nanocolumns or nanoneedles. So it is spontaneously grow and creating film, which where each nanowire touch each other to form a conductive network. So finally, this film is well conductive and used for gas sensing. So we obtain it, for example, higher response to gases, and as well lower working temperature, where the gases are, where the sensitive films are more sensitive to the gas. So it was significant decreasing of the temperature. As well, this temperature means that we decrease the power consumption of the device. To characterize single nanowire, this was as well our aim to see how the single nanowires how the property of single nanowires, how is working or its role in this conductive network. So we created this on-chip platform to characterize single nanowire. And this single nanowire was deposited by electrophoretic separation. And we measure in the gas. For example, we decorated nanowires and compare with undecorated, as you can see in this picture. So we have some results with this type of nanowires where the selectivity was increased, because probably you know that the selectivity is the problem in this case of semiconductor chemoresistive sensing elements. But the advantage of this device or single nanowires is it's self-heating, because if you apply any measurement current, so the nanowire is heat up during the measurement. So it can be advantageously used for the heating to the operating temperature. And you can imagine that the power consumption will be very, very low in comparison with standard devices. So it will be in microwatts, not milliwatts, in case of standard. So these some results, not so old. And last part is focus on nanodots and as well quantum dots, which are more to topic. So this is for the biosensing. We used several chemical synthesis or template-based technique to grow these nanodots. The quantum effect is observed in some materials when the size is below 20 nanometers. And by the size of the quantum dots, we as well change the wavelengths of the emission. Semiconductors are mixtured semiconductor used in synthesis. So we created cadmium telluride or cadmium cyanide quantum dots, as well the carbon-based quantum dots. As well, we deal with core shell structures, which is more stable. Some stabilization can be done with the modification of the quantum dots, as you can see here. There is as well some significant shift in wavelengths according to modification, which as well helps to stabilize the quantum dots and helps for the bioprobe formation. So because these quantum dots are mostly used for bioprobe, for bioimaging, so the surface of these structures or these nanodots has to be modified or conjugated with biomolecules with high specificity. Then can be used for example, to observe exactly the cancer with high specificity, as you can see on this mouse. And last, quantum dots in bioanalysis, some example where we used bioconjugated quantum dots with antigens for detection of bovine serum albumin and mouse immunoglobulin. We use the on-chip application and electrophoretic separation. And finally, the optical detector with filter. And the quenching effect of the quantum dots was used to detect these antigens. So here are presented some result for bovine serum albumin. And of course, there is some limits in detection. And it was just to present that this cheap technique can be used for here to antigen recognition. So thank you for your attention. Of course, some acknowledgement to our Horizon project and Czech Nanolab project from Czech government. And now is open it for your question.
Thank you, Jaromír. So if you have a question, please raise your hand. Maybe I can ask regarding the gas sensing properties, which gases you were aiming for with the structures, with the nanostructures of metal oxides?
There are several gases, ethanol, CO, hydrogen, ammonia, and others, and O2, for example. So the toxic gases are the most, and as well some dangerous, so flammable gases. But everything depends on the material. So we try a lot of gases to find which gas are preferable detected by the material and structure.
And how can you tune the properties of the layer to make the layer selective for certain gas?
Yeah,
is it possible?
So we found several interesting properties of nanostructures. So, for example, the shape can impact the sensitivity, as well the sensitivity to interactions with the humidity. So because the humidity has to be avoided mostly, so for example, some type of nanostructure has less sensitivity to humidity than others. And nanodecoration, so some catalytic particles can be simplified used, as I demonstrated. So this improved the sensitivity, for example, to ethanol in case of decorated, contra undecorated, which are more sensitive to NO2, for example, in case of tungsten trioxide nanowires.
Okay, interesting. Thank you very much for your presentation.
You're welcome.
There's one more question from Magdalena Šimke, please. Magdalena, we cannot hear you since you are muted.
Sorry. Do we still have time, or you want to move on to the next presentation?
Yeah, I think that we have time for one question.
No, just very briefly, because you were showing some mouse experiments where you used the nanotechnology developing for cancer detection. I was wondering, as I have been previously working with nanodiamonds, and we were debating a lot about biocompatibility of nanostructures and nanomaterials. Do you know how or what was the determination for your nanomaterials being used in mice with respect to the biocompatibility or toxicity, potential toxicity to the animals?
Yes, of course. In my team was people working especially in this topic. So to observe the cytotoxicity of the nanoparticles, such this, not only this nanodots, but many others as well. And of course, without any modification of the surface, it's toxic. These materials are toxic. It's clear. So, but the encapsulation with, for example, there was used now GSH, for example.
Okay.
These materials helps to eliminate this cytotoxicity of these particles.
So, but they were coating the particles with proteins to make them compatible.
Yes, especially as well this modification, let's say, or functionalization improve the modification with some antibody antigens for detection. So it is as well advantage of this covering or encapsulation.
Thank you.
Thank you again for your presentation. And the next presentation with title Planar Electrode Structures for Sensors will be given by Michal Bodnar, R&D Senior Engineer at the company Tesla Blatna. So, Michal, the floor is yours.
Hello, everyone. I try to start my presentation. Do you see it? Hear me?
Yeah, we can see it well, yes.
Yes. Okay, I'm Michal Bodnar from Tesla Blatna. I am head of our thin film laboratory, and we produce and develop planar structure for sensing and gas sensing application, or for chemical or biological application for university and other company. Now we have many project with university and research institution in Czech Republic, especially. But we had two projects, European project for developing gas sensing in a few years ago. I want to briefly introduce our company, and then I can show you, and I will show you what we can offer for sensors, biosensors, and other application in nanotechnology. Okay, Tesla Blatna is company from South Bohemia. Now we have about 300 employees, but it's still we have 3 different parts in our production, and it's very interesting for the sensitive application, because we have not only thin film layer and this type of structure, but we have electronic research department, and we are able to connect these two parts together. And if we have or we can see new application in this area in sensors, we can prepare not only chips, but only develop new electronic detection principles. So this is our typical three steps, 3 parts in our portfolio. We produce electronics for battery management, from hand tool machines, from electronic motors. One interesting part, and still interesting part, is automotive application. For us, this is in ignition cable. It's not for you, but I can shoot what we produce, and then it's our application is my application is sensors and sensors platform. Here you can see our typical how we divide this our portfolio. Our technology, we start with the sensors about 10 years ago. We built new clean room laboratory. Tesla have many and big strong experiences with thin film layer, but not for sensors, but for microwave application. Then we transform these experiences and the people into sensors application. Here you can see old evaporation machine, which we use still for optoelectronics resistors application. Now what we have, we are able to offer for you, or for everything, for everybody, our machine, our technology for about sputtering. We use dye etching because we sputtering platinum. It's our basic material, and we use the ion etching for this material. Then photolithography, it's up to 1 microns. It's typical our dimension. And then we have complete thin film technology, from trimming laser, basing saw for splitting the substrates, and then I don't know, welding machine for contact wires for another application into electronics, etc. Then we have for calibration gases. We have 1 lab with very specific setup for calibration. I can show you. This is few picture from our laboratory. You can see for screen printer dispensers for our application. We use it for print or take few points of platinum layer. This is welding machine for welding wire for our platinum or planar structure, and thermic laser. It's for platinum temperature sensors. It's one of our main product from our laboratory. Here are other machines and devices. Sputtering machine. It's old machine, but we are able to sputter platinum, gold, nickel, chromium layer, etc. Then on the right side, you see our gas sensors equipment for calibration and for measure sensor structure. Technology, what we use, one more time, it's about we sputtering metal layer. We prepare this layer for research institution or for us, and with our colleagues, we use this especially for gas sensors, developing with new material, nanomaterials, single wall nanocarbon tube with some dopants or some another material. What we use ceramic substrates from ceramic, silicon wafers, and glass substrates. It's our typical substrates. Sometimes we are able to produce electrostructure on flexible material. You can see here the Kapton foil. What we can offer and we produce, it's this few electrostructure or temperature sensors we use for our research and another application. Integrated structure, it's typical and basic structure. Then our main product is platinum temperature sensors, and we are able to produce very different ohmic value, or for one company we produce temperature heater with about 80 ohms, and it's the same like temperature sensor. It's the same parameters and properties, but they use for hydrogen sensors. Then we produce multi-sensors platform with its combination about interdigital structure plus heating element and temperature sensors. It's good for if you need control temperature of your layer and measure in the same time the smaller and some cheaper maybe. It's combination that the interdigital structure are on the one side, and the bottom side is the heater element. There is no temperature sensors. It's smaller and they have better temperature distribution on the layer. Then we produce electrochemical sensor platform with very different electrodes. It's one example of this structure. What we final product for us it's humidity sensor with specific sensor slider. It's we use for this the application of the sensitive layer our screen painter. Then gas sensors with metal oxide. It's for detection ammonium, nitrogen dioxide, etc. And then here we use sputtering machine for sputter the sensitive layer. Then we still develop and testing our new sensors with single wall nanocarbon tube and multi-wall carbon tube, carbon nanotube with dopants of indium tin oxide. It's typical for us for our research, and we have one sensor for nitrogen dioxide or nitrogen sensors with electrochemical sensors. Here you can see our results with indium tin oxide. Here you can see on the sensitivity on methane. Then you can see the carbon dioxide. It's this type of layer have good sensitivity, and the responsibility is very good, and the response time it's good enough for our application. Here you can see our customization. It's a combination of research and product. You can see conductivity sensors, holes for electron beam microscope. Very interesting. It's two electrode structure, interdigital structure for comparing measurement for biology and chemistry. Here is the tile with this structure. There's two same structure, but you can measure compare. One is sensors layer, and one is the reference structure. Typically, in all this construction, this is constructed with two layer, nickel-chromium layer. It's under the gold layer with 1,000 nanometers. Yeah, we are able to produce this one. What we have, and we our company has currently 5 running research projects supported by from Czech Republic, and for this project, the topic is around nano materials. One is I hear nano diamonds. It's one of our topic in our research from Ministry of Education, Young and Sport. On this start, I talk about our electronic development, and we can produce and develop very complex solution. Here you can see one of these results. It's environmental module. Inside this box and case, we have 13 individual sensors with four gases: temperature, humidity, pressure, light, etc. And it's very complex product from Tesla. This is the second very complex solution, but it's it was stopped in prototype version. It's suited for fire brigade. That inside is gas sensors, humidity, temperature sensors, and position gyroscope for detect the move of the fireman. Okay. In conclusion, Tesla produce a various sensors application. We cooperate with many companies that they want to from us produce different temperature sensors, different electrostructures on the very different substrates. You can see here the hydrogen sensors in the aluminum cases for explosive area, or temperature sensors where inside is our ceramic platinum temperature sensors. Yeah, it's and our laboratory or our company we can produce chips from units, pieces to several hundred thousands per year for everyone. And it's thank you very much for your attention. And if you have any question about our products or our develop. Sorry.
Thank you, Michal, for a very interesting presentation. I've some experience with your platforms, so I know your products, but there are for sure some improvements over the years. So let's give a chance to ask someone else if there are any. I would have maybe just a very short question if nobody else is asking. Is there any room for, because you are using mostly screen printing in your technologies, is there any room for inkjet printing? I mean, for digital processes to deposit materials, either conductive or sensitive in the future?
Yeah, in one project we use inject machine for sensitivity layer on this electrostructure. Yeah, because the liquid substance with nanocarbon tubes, it's difficult to transform from liquid to the layer, and one institution use inject machine for this one, for this application. Yeah, because it's cheaper than another material. Somebody use drop coating or something like this, but maybe for us the inkjet is better and the homogeneity of each sensors will be better.
We can talk also later. We can offer something for you. Thank you very much for your presentation.